Wonderful. And our next speaker is Oliver Schneider from the University of British Columbia, and he's going to be talking about tactile animation by direct manipulation of grid displays. So take it away.
Thank you. So I'm Oliver. I'm from the University of British Columbia, and this work was done with Disney Research. I'd like to start with a bit of a question. How many people have ever been lost and used their phone as a GPS to find their way? Oh, come on, more than that. Yeah. Everyone's done this. Now, this is not always the best solution, partially because there's a lot of environmental disruption that could happen. So if there's loud conversation or music in the car or other environmental concerns around the car, this means that you might not hear the instructions of where you're going to go. And of course, looking down at the screen can be quite distracting and dangerous even. So you can imagine that doing something like tactile feedback might be able to help in this situation, where your chair could vibrate to tell you to take the next left turn, for example. And so people have looked at this with a new class of wearable devices that take multiple actuators on the person. And these are vibrotactile actuators, so they vibrate, and you feel that through your skin. So these are the other mechanoreceptors that wasn't talked about in Impacto. And so this does indeed help people drive in a way that's less distracting, which is great. But it's not a very expressive system. You only have the 3 actuators, and so you can really just tell people when to turn. Not much else. So what happens if you want to warn people about upcoming problems with traffic, or if you're backing into a car, slow down? Well, you might turn to something like this, which is a grid display, which is a lot more expressive. And the reason it's a lot more expressive is for 2 reasons. First, you have more actuators, so there's more that you can actually display. But also because you can take advantage of haptic illusions. And so looking at the tactile brush algorithm, we can talk about 2 such illusions. The first is phantom vibrations. So if you take 2 actuators and you vibrate them at the same time close together, you actually only perceive a single sensation in between them, a phantom sensation, a phantom vibration, which means that you can get in between the actuators on these grid displays. The other is if you have a series of actuators and you activate them in sequence with just the right timing. So if you do actuator 1, 2, 3, just right, it feels like a single continuous motion across these different actuators. And so now you have a lot more expressive of a space. So this means you have a really expanded design palette, and you can start to use things like arbitrary location and motion on the back, which really enables you to do more interesting things. So with our driving scenario, allows you to be a little more sensitive to driving locations, allows you to tell the driver more. But you can also imagine other applications. For example, accessibility, maybe using a vest for visually impaired people, or immersive media experiences. And I'd like to thank Pedro for setting this up quite well. There's a lot you can do when you have haptic feedback. Now, to be able to create something this engaging, you need to be able to actually create the sensations and the content. And creating the media content is challenging because right now you have to program and set up all the devices yourself. There have been a couple haptic design tools, but very few of these actually handle multi-actuator displays. One of them is called Tactile, and this allows you to sequence these actuators. But this is quite limited when it comes to grid displays. Because if you're saying actuator 1 vibrate for 1 second, actuator 2 vibrate for 2 seconds, and so on, then you can't really start to use these illusions as part of your design palette. Instead, you have to start to figure out those algorithms on your own, and this can be quite a problem when you're trying to be creative and dynamic in your design. We might want something more like tactile movies, which is if you have a rectangular grid of actuators, you can treat them like pixels, so taxels, as we've already talked about earlier today. And this lets you, you can draw lines, and it translates into these actuators quite nicely, but once you start to iterate in your design, things are a little bit more challenging, because if you have to edit each actuator on its own. And so coordinating the gestalt of an entire sensation can be quite challenging. This is further hindered by the fact that Tactile Movies works in frames, which is great if you're working with video, but if you want to create something that's interactive or you want to create something that doesn't quite map to video, it can be challenging as well. And it relies on a rectangular grid, so that's less applicable to body-size displays and wearables. For example, the seat of a car or a vest. So instead, we might want to draw from visual design. And how do people work in visual land? Well, they use tools like Maya and Blender to create motion and to animate and create dynamic effects. And that's what we want to talk about today, is tactile animation. How can you use these ideas to actually create animated content and enable artists and designers to create this animated content for all the applications that we're seeing in this session today? So this is the concept of our workflow. You start with an animation tool, which allows you to edit these tactile animations the same way you might do for visual content. We then have a rendering pipeline, and then we propose one rendering algorithm, but you can sub in your own depending on your target device. And this will output to whichever device you're hoping to work with. Now, we didn't come up with this concept out of thin air. We talked to a number of haptic experts and media creators to come up with this idea. And we came up with a preliminary design based off of existing, it's not showing up very well in that resolution, a preliminary design that was based off of existing visual animation tools and also existing haptic tools. So let's show you our prototype. We call this prototype Mango. The top of it is the spatial display, so you can see a grid as well as your phantom sensations in between those actuators. And down below, you have a timeline, which allows you to actually sequence and animate them. So let's see it in action. And before I play this video, I just want to mention that everything you work with this tool in playback and when scrubbing around is felt in real time, and so you can actually design experientially. So these purple circles are phantom sensations, and you drag them around, which updates the grid. You can resize them, and this changes the intensity, so now you have control over the intensity. You can sequence them by moving them in time and scrubbing around to feel what they feel like. You can change duration, and you can type in parameters to change the location and the size. We also include keyframes, which is essential to animating. By adding these keyframes, we can interpolate in between them, and this allows you to get some smooth content to actually create a fluid display. You can add paths, which allow you to very easily create pre-made shapes. So this is a line, for example, just by constraining the motion to the path. And for completeness, we also include what we call a vector sensation, which is working with each actuator as an array of values. And so you can animate this in the same way that you work with tactile animation objects. This was also used for comparison in our user study later on, because it's similar to previous results. And so the trick is this animation object, this abstracted notion of a phantom vibration that goes in between these actuators. Now, how do we actually get this vibration to work? How can you directly manipulate this in between the grid? Well, we have to have a new rendering algorithm for that. Now, a lot of work has been done on understanding interpolation between two actuators, so this is fairly well understood. You can create a sensation somewhere along this and indeed create motion in between these, as I've already talked about, depending on how intense the two actuators are. We extended this to 3 actuators, and so now you've got interpolation within a triangle. We use barycentric coordinates that we then scale to make them perceptually salient. And once you have a triangle, you can go to a mesh, and this allows us to work with arbitrary planes and 2-dimensional shapes. We ran a user study with this to look at 3 different models. These are the models that work well in 1-dimensional 2-actuator interpolation. And we found that with 18 participants, we found that the logarithmic scaling was the best for creating a straight line motion. And so that's what we use for our evaluation, which I'll get into now. So our evaluation worked with this pad right here, which is a grid of voice coil devices. We recruited 6 participants because we wanted very rich qualitative feedback. This allowed us to really understand whether this paradigm of tactile animation was working to enable design, and also what could help in future iterations of our tool and future tactile animation tools. Of them, 4 of them were animators. 5 of them had animation experience. 4 of them were professional animators. So we got to actually get a sense of the expert's opinion on this. We trained them on our tool, and we gave them 3 different tasks: create a heartbeat, create a sensation that tells someone to turn left, for example, in a car, or to match this sound. Chosen because it's awesome, but also because it's a little bit complex, and it would encourage something a little more interesting for design. You've got a descending pitch, which might be spatial in nature, and then you've got that crunch at the end, which is more temporal. And so it doesn't bias either the animation objects or the individual actuators. So in our evaluation, all participants within their 1-hour session were able to accomplish all 3 tasks, as well as a post-interview and their training. And the tasks were completed to, they were happy with the results. It was their satisfaction. And of course, people relayed this to an animation tool, saying that, this really is animation. Now, we went a little bit further than just saying, okay, could people design with this? We tried to look at what we could inform for future tools. One was a comparison between animation objects and these vector sensations, controlling each actuator on its own. And people heavily preferred using the animation objects. Of all the designs, only one of them was done entirely with vector, and I think only one other one was done with a vector in the final design. So participants almost only used animation objects. But this is a little more nuanced, because animators expected that while they preferred animation objects, they also thought they would be more accessible to people who weren't animators. So because they're experts, they could kind of work with the vector sensations, but it was definitely more accessible to other people. And was able to control more of the area at once. So it was a little more powerful. So we encourage people to maybe keep this in as an additional feature, even though the animation objects worked quite well. Now, direct manipulation, which is the key value of having this rendering algorithm work in real time, was important. People would play around with the animation objects to help them brainstorm and help them come up with their designs. And so they do something like this. And remember, they can feel the feedback as they're working with it. They would drag around these sensations to find the right location for the heart when making their heartbeat sensation. They would try and act out the left turn to see what would make sense. So this really did enable creative playing with the sensations, which is great. It'd be very hard to do this with just the actuators themselves. And in fact, this idea of experiential design was very important, not just for being able to feel the sensation in real time, but also people would check their pulse to create their heartbeat, or try and find the location on their chest where their heart was to get it just right. And one person even brought up YouTube to be able to get the heart sensation just right. And so we think that even more experiential design could be valuable in future tools. So people could, try something out in the tool, then go and research either from their own experience or from videos, and in this way, very iteratively do design. Finally, we observed lots of replication. Our prototype did not include copy and paste, which was a good thing because we found out how important copy and paste was. 5 participants asked for it, and lots of people did replications, both in time. So one participant actually refused to do their second heartbeat because they didn't have copy and paste. They said, oh, I would just copy and paste that. But also in space. So people did lots of parallel lines and multiple animation objects. And so we think that more powerful replication tools like looping or groups would be important in future tools. So it seems like tactile animation's a pretty promising metaphor, but does it generalize? Well, remember that bracelet device from before. If we use one-dimensional interpolation instead of two-dimensional, we can collapse tactile animation objects to linear displays. And so we can cover previous devices handled by previous work. We can also look at 3D applications. You can imagine having a surface embedded in a 3D tool like Maya or Blender and dragging these animation objects around on the surface, which really opens up a lot of possibilities for design. In addition, you could look at multiple devices. So going back to our driving example, if people are driving and you really want to get their attention, if they're very distracted, you could work with the steering wheel as well as the chair. And so we think that this tactile animation naturally supports this as a use case. And in fact, it supports more than just vibrotactile feedback. So there's a new range of devices which use ultrasound for mid-air haptics. So you can feel invisible haptics on your hand at a distance. And it uses localized points to do this. As long as you can come up with this abstracted notion of an animation object, something you can drag around and work with, you can use tactile animation. So we think this is a very promising technique. So tactile animation enables continuous, direct manipulation through 2D interpolation. Through our evaluation, we found it was an accessible and powerful metaphor for haptic design, and has the potential to generalize to different devices. So we think that this is a good way to go. Of course, there's more to be done. We plan on scaling tactile animation to additional virtual reality and augmented reality situations like we've seen today, build content to actually understand what content needs to be designed, and develop new techniques for haptic design. So if you look at really expressive tools, this is what we're trying to do, is we're trying to give the artist a really fluid, creative palette of tools to work with the sensations that they want to create. And we wanted to create not just visual content, but new immersive virtual reality content, like this, which is another kind of phantom sensation felt in between your hands. And you can imagine animating this with powerful creative tools. Thank you very much, and make sure to come and check out our demo tonight.
Great. So we have time for questions. So again, just raise your hand and the SVs will come over. But I'll start with one. What really cool work. I'm wondering if you guys thought at all about like programming by demonstration. So either directly like on the body, like having some tactile sensing, or just through a multi-touch or pressure-sensitive multi-touch input device.
Definitely thought about it. I have a number of concepts that I'd like to explore, and we've looked at touch screens as well. So you can just kind of sketch around what you want to work with. It's definitely something to look at when it comes to physical land, but we want to get the pipeline ready first, so that's sort of where this goes, but definitely the next step, I think, or one of them.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I was a little bit disappointed you didn't tell us the results of the awesome sound, and I'm curious what people did for that.
Well, I can tell you about it now. The awesome sound, the video that we have online, there's an extended video that shows all the designs that every participant did, so you can see some of the cool things that they did. But the sound is interesting because people loved it. When you're presented with some sort of stimulus to design for, people just kind of run away with it. Everyone rated it 5 or even 6 on our 5-point scale, saying they loved working with it. And got visibly excited, even if they weren't they were reasonably excited before, but the sound really drove it home. And so in follow-up work, which I can tell you about if you come find me after this, we've definitely been using stimulus like that and visual animations to try and encourage design. So I definitely recommend using sound or visual stimulus to kind of as the task, because people love it.
So something I wanted to try to get a sense of is how hard it was for them to do something complex like that, because I can imagine if I wanted to do something like that, I might have multiple pulses going here and there, slightly offset, and then gathering to one big pulse at the end or something along those lines. But like, how hard was that? How long did it take them to do complex things?
Right. So the average time for all of the tasks was about, I think it was 8 minutes. It varied, I think, from about 4 or 5 minutes to maybe 12. The details are in the paper, but it was, actually reasonably quick. Now, time is not a good metric for design, because sometimes people like to iterate quite a bit, but everyone was pretty happy with what they created in such a short time period, so we think that it's definitely got potential.
Cool. Thank you.
So we have time for about one more question, if there are any, but I'll ask one while we're waiting, if there's any other. So one question about your now 3-point rendering algorithm, and sort of also the perception. How disparate would these tactors need to be such that you could have 2 simultaneous sensations? Obviously, if they're very close, then you perceive these pseudo haptic experiences. How far would they need to be, and your system, analyze that to sort of show you, oh, these are, going to overlap, or these would allow you to have 2?
Right. So we didn't study that specifically. There's a lot of areas for exploring this more perceptually, but definitely you can have them on different parts of the mesh, and it seems to work fairly well. At some point, the actuators saturate, so you could imagine showing that visually, because if designers are working with it, they can maybe accommodate that and have it become a sort of blob if it's starting to saturate. Definitely an area that we want to look at next is more of the perception. But also, the nice thing about this is it can be used, even if the perception starts to saturate quite quickly with this 3-dimensional thing, You can imagine it as sort of a pre-fill exploration stage, and we can use more sophisticated rendering algorithms like tactile animation tactile brush or other ones that are developed in the future, even if they have to be computed to accommodate for these issues as sort of a final render. So even when the rendering algorithm falls short, you could use it as sort of a previs situation. So we think that there's ways of accommodating that both in the interface and also, to build upon it for future work.
Great. So I guess with that, we will thank the speaker